Hi, I'm Oriol and I'm affiliated with the Instituto de Robótica e Informática Industrial. I'm part of the ALICE PhD program. I'm happy to present you ProcSim, a work that I did while interning at Amazon. In this work, we propose a robust similarity learning algorithm that uses confidences computed from a proxy-based metric. Learning visual similarities requires labeled datasets, which in most cases have been annotated by non-experts in crowdsourcing platforms. This inevitably leads to errors. As an example, let's try to annotate images showing animals. This may seem an easy task, and it might be so for some instances. Here's a giraffe. And here are a couple of seals. Oh wait, that was actually a sea lion. You can now see that annotators are prone to committing mistakes, and it is natural that this happens between similar classes. In other words, mistaking a sea lion by a seal is possible, but doing so by a giraffe would be odd. The problem is that deep metric learning models suffer a higher drop in performance than classification models when there are annotation errors in the dataset. The reason for that is that DML considers interactions between samples. Due to the wrong annotations we had before, we may force the model to learn wrong similarities by creating wrong pairs. In this case, a positive pair between the seal and the bad annotated sample and a negative pair between the correctly annotated sea lion. Mistakes are very common, and in particular for the CAP dataset, which we use in this work, it is estimated that at least 4% of all labels are incorrect. Knowing that there are some wrongly annotated samples in our dataset, we propose to compute a confidence score that scales the loss for each sample. Doing so, we also scale the gradients, and the contribution of a sample is reduced if it has a low confidence. One very simple solution to spot labeling mistakes is a so-called small loss trick, which is based on assuming that a large sample loss indicates a label that is likely to be explained by the current model and may be wrong. However, this trick has to be used with caution because it does not work on all losses. In this example, we tested two DML losses on a dataset injected with noise. We can see that the proxy NCA is quite good at separating noisy samples, but multisimilarity loss isn't. To determine how to compute the confidence sigma, we apply some desired properties. First of all, we want sigma to be translation invariant with respect to the loss, meaning that if there's a shift, nothing happens. We also want the confidence of samples with lower loss to be higher, and this is based on the small loss trick I introduced on the previous slide. We want the confidence to be constrained between 0 and 1. And finally, we introduce a hyperparameter, lambda, that controls the severity of the confidence. This interpolates between completely discarding noisy samples to considering all samples equally. Let's now see how ProcSim works. We have 4 images from the CAP dataset, and the blue one is wrongly labeled. The DML model ingests these images and creates some embeddings. In the embedding space, we have one proxy for each of these classes. In this case, we have one for lace and albatross and one for crested auklet. And we can see that the wrong label is closer to this, but the labels are used to determine the correspondences. There's one wrong, and when computing the proxy loss, we can see that the sample with a wrong label has a higher value. Once we have computed the proxy loss, we want to determine some threshold to tell apart clean and noisy samples. To determine this threshold, we use Otsus method, which starts by sorting all the values of loss proxy. Then, we test all thresholds that separate consecutive samples, and select that one that minimizes the intraclass variance, in this case, the upper one. This threshold is then used to compute the confidence, which uses the following equation that satisfies all the previous criteria. And we can now see the effect that different values of the hyperparameter lambda have for this problem. And we finally reach the full loss of ProcSim, which has the confidence that we computed before, scaling the DML loss, which uses labels to learn similarities. The confidence score is used as a constant, meaning that the loss is not propagated back to proxies. Finally, we include a self-supervised loss term with regularization parameter omega. When assessing the robustness of DML models, datasets are corrupted by swapping some labels. This allows controlling the noise level and knowing which samples are incorrectly annotated. In the literature, the corruption is usually done using the uniform noise model, which is based on swapping labels uniformly at random for some portion of the dataset. However, this noise model is unreal. If we want to inject noise to the example animal dataset, this noise model could swap the classes of giraffe and seal. However, we are interested in replicating semantic confusions, so that the performance that we report on the corrupted dataset is as close as possible as the one we would achieve in a dataset with real annotation errors. To do that, we compute a class hierarchy using WordNet, which provides a semantic relation between class names. This is how the class name hierarchy looks like for the cup dataset. We can see that at the center we have the superclass bird, which is the root of the hierarchy because all the images of the cup dataset show birds. As we move to the exterior of this circle, we can see some classes of birds, and finally at the leaves we have the class names. If we move closer, we can see an example of how noise would be injected. Here we have the black-footed albatross, and one image of it. This bird is a type of albatross, similarly to the Suri albatross, and here is an image of this bird. The cup dataset also contains Florida jays, which belong to another family of birds, and do not share as many similarities with the other two images, as we can see here. The noise model that we propose is based on swapping labels between images from the same family. So in this case, the Suri albatross label could be swapped by the black-footed albatross label, but never by the Florida jay label. Now, let's analyze the results of the evaluation, which we perform on the cup dataset corrupted with different levels of the proposed semantic noise and the commonly used uniform noise. We also include the harmonic mean as a measure of robustness, which aggregates all the performances and penalizes deviation from the mean. We can see that, although the confidence computation of this work is similar to superloss, ProcSim and all their variants, which we show in green, are vastly superior to it for the task of DML on noisy datasets. The models trained without sample confidences show that multisimilarity is a better loss to train the DML model. However, as we have seen, Proxy-NCA is much better at spotting noisy labels and shows better robustness to increasing levels of noise. For this reason, the base version of ProcSim uses the multisimilarity loss as supervised loss and the Proxy-NCA loss for the confidence computation, getting the best of both worlds. Among all ProcSim variants, we identify these ones in red as the major drivers of performance. The first of it is using a powerful supervised loss, and the other one is to not scale the self-supervised loss by the sample confidence. In this way, when we have a sample that has a very small confidence, the self-supervised term will dominate and be useful to resolve interclass similarities. In this table, we compare the performance of ProcSim and two state-of-the-art methods for robust deep metric learning. We can see that the results of the Bastan for a light product dataset for both the semantic and uniform noise models are very similar. That's because there are only 12 categories on the SOP dataset, and many instances of each of them. This means that our noise model is essentially assigning a label uniformly at random from roughly a 12th of the dataset, which is not that different from the uniform noise model. As you can see indicated in bold, ProcSim, our method, achieves the state-of-the-art performance in all cases. Another observation is that the other approaches, especially the MCL plus PRISM, observe a higher drop in performance when noise is injected following our noise model. The results show that semantic noise can be more harmful as it generates samples with wrong labels that are harder to spot. Instead, ProcSim shows the opposite behavior, which we attribute to the resolution of interclass relationships thanks to the self-supervised loss. In this paper, we propose two major contributions. On the one hand, we introduce ProcSim, which achieves state-of-the-art results and is a novel framework for robust visual similarity learning usable on top of any general purpose DML loss to improve the performance on noisy datasets. The only requirement is that the DML loss has to be sum-structured, so that the loss term for each sample can be independently scaled by the confidence. On the other hand, we also introduced a noise model that yields more realistic errors. These labeling errors are harder to spot, and the results obtained on the datasets corrupted with them better reflect the real robustness to semantic errors. And here are some take-home messages from this presentation. The small loss trick is useful, but we have to be careful about which losses we are using it on. We needed to separate clean and noisy samples and use also threshold method for that. This method is a one-dimensional discrete analog of Fisher's discriminant analysis and selects a threshold that minimizes the interclass variance, or equivalently maximizes the interclass variance. While this algorithm is typically used to perform image thresholding in classical vision, it can also be used in other problems, as it does not require any optimization, has no hyperparameters, and achieves the same result as globally optimal k-means. We also saw how annotation errors can easily happen, and that the reason is typically due to semantic mistakes. For this reason, we have to consider that real noise is a structure, and methods that are robust against uniform noise are not necessarily the best for real uncurated datasets. Finally, we saw that by reducing the gradient update of low-confidence samples, we can consider them in training by means of a self-supervised loss term and a supervised term with decreased contribution. This turns out to be better than completely discarding noisy samples. Feel free to check the full paper on the WACP proceedings or on arXiv, and do not hesitate to send me an email if you have any doubt or suggestion.